what I'd like to do today is sort of introduce you to some trig and talk in particular. I'm going to start with the unit circle. And you might have wondered why this thing was so important, right? So hopefully by the end of this you'll be convinced, hey, this unit circle is actually pretty handy, right? So what is the unit circle? It's the circle centered at the origin, 0, 0, with radius 1, okay? So it's easy enough to draw. Here you go, right? And you can name some points right away on this thing. Oh, that's the point 1, 0. Here's the point 0, 1. Negative 1, 0. And 0, negative 1. Okay? And you might even know something about the equation of this thing, right? The equation here is x squared plus y squared equals 1. Okay, I don't see any trig yet. You're going to have to wait a little bit. For those of you who are not clear about equations of circles, they're sort of, if you look at it for a minute, it almost looks a little bit like Pythagorean theorem, doesn't it? You've got something squared plus something else squared equals 1. Well, 1 in this case. But that 1 squared is 1. So it looks like a Pythagorean theorem. Let's talk about why that works, right? So let's just imagine a sort of a silly story for a minute. So let's pretend I am standing right here at the origin. I'm standing at the point 0, 0. And I am a person who can be a little weird to stand near. Here's my example. Okay? You stand too close to me, I don't like it. I feel like you're invading my personal space. But if you stand too far away, I feel like you're not interested in talking to me. It feels like you're trying to avoid me. Right? So it turns out for me, the perfect distance to stand away from me is 5 feet away. Okay? So I'm going to go out over here. I'm going to say, here I could definitely stand out here. If you stood here, I would be happy at the point 5, 0. Right? You could also stand up here, 1, 2, 3, 4, 5, at the point 0, 5. Right? Okay? And then you can stand here at the point negative 5, 0. And you could also stand here at the point 0, negative 5. And if you stood at any one of these 4 points, I would be happy. You should be at the perfect distance you were away from me. Any closer, I'd be upset. Any further away, I'm going to be upset. Okay, strange behavior. All right, let me remind you of something. I want you to think, a long time ago you learned about something called a 3, 4, 5 right triangle. Right? I mentioned it now because we could go 3 units over. If I went 3 units over and then 4 units up, I would land here at the point 3, 4. And this distance would be 5. Right? How do we know that? Because we know that 3 squared plus 4 squared equals 5 squared. Okay? Well, if 3, 4 works as a point, so does 4, 3. So you can be here. Okay? And then that would also be 5. So here I've got 2 more points you can stand at. Well, I'd be okay. Right? What else would work? Well, how about back 3, up 4? So negative 3, 4 would work. And how do I know that? Well, negative 3 squared is positive 9, and then positive 4 squared is 16, and so forth. You'd have the rad of 25. And so would negative 4, 3. Okay? And what you start to see now is if you start to trace through these points, just see, wow, that does look like a circle. Okay? But here's the fun part. If you look at these points, what you'll notice is, like look at this point, if I did 5 squared plus 0 squared, I would get 5 squared. Over here, if I did 4 squared plus 3 squared, I get 5 squared. Here I would get 3 squared plus 4 squared equals 5 squared. And my claim is that those are all Pythagorean theorems. Watch. Here's a Pythagorean theorem with that triangle. Here's another Pythagorean theorem with that triangle. So it's sort of like a quick justification as to why your equation of circles look like Pythagorean theorems. What I'm really saying is you can stand anywhere you want as long as you're 5 units from me. So I'm fixing the distance. I'm fixing all these distances to be 5. And if you think about that, that's sort of like saying, hey, I want the radius of the circle you stand on to be 5. Okay? Back in this example, we wanted the radius to be 1. Okay. So let's continue. Let's go back to this unit circle. I'm going to draw it a little bigger. I'm going to make one claim, and then the story of how the unit circle is so important to trigonometry will maybe become a little clearer. Okay, so here's your axes. This is going to be our unit circle. So this is the point 1, 0. Here's negative 1, 0, and you know the rest of the points. Okay, so here's the question I'm asking you to sort of believe, or I'm asking you to think about. Let's concern ourselves with this angle. If I draw this red line, if I draw this radius in, my claim is that radius makes an angle with the x-axis. Okay? Sure. Now, here's what I want you to believe. If that angle were a particular number, the way I've drawn it here looks like it might be about 45 degrees, then it would correspond to a particular point on the circle, x comma y. Right? Now, if I were to make theta bigger, if I drew an angle that was slightly bigger, maybe made it all the way like this, then my claim is it would correspond to a different point on the circle. So what I'm asking you to believe is that every time I change theta, it's going to correspond to a new point on the circle's circumference. Right? And additionally, it's going to correspond to only one point. In other words, if I pick an angle like this, I take a small angle theta, and I draw the radius out, it's going to hit the circle's circumference at one point only. Okay? So I'm mentioning this because what that means is that every point on the unit circle, okay, would have a unique value of theta. Or I'll say it this way. For any theta you choose, there'd be one point on the circle's circumference. So what this means is that if I know theta, then I should know what point x comma y I'm at on the circle's circumference. So given theta, we should be able to figure x comma y. So let's draw one more unit circle and see what we can do. So again, we got a unit circle again. Here's the point 1, 0. And we're going to pretend for a moment, we're going to say that theta is known. That's what we're going to start with. Theta is known. So let's pretend we draw this picture, and we know this angle here, theta. My claim is we actually know the coordinates of this point, x comma y. So to show you, what I'm going to do is I'm going to make a right triangle for us. Here we go. Here's the hypotenuse. There's one of the legs. There's the other leg. Now that we have this triangle, we just got to come with some good names for the sides of it. I claim a good name for that would be x. And you know that because to get to this point here, you'd have to go right x. How far up would you have to go? You have to go up y. And now we're ready. So we actually know the hypotenuse, 1. Okay? By the way, do you see the equation of the circle? X squared plus y squared equals 1 squared. Pythagorean theorem, right? Okay, but what else do we know? Inside of right triangles, we also can use our trig ratios, the sine, cosine, and tangent ratios. And that's what I'm going to do. My goal is to get a ratio that has x in it. So I'm going to use cosine. I'm going to say cosine of theta. Forgive me for a second there. Cosine of theta is equal to the adjacent x over the hypotenuse 1. Well, now you can see the convenience of having a hypotenuse of 1, right? Now you know that x is cosine theta. You can see the prettiness of having that radius be 1. All right, let's do sine of theta. Sine of theta equals y over 1. Well, there you go. That means it's just the y value. And we have shown that my claim was true, right? That if you know theta, you know the point on the circumference of the circle that corresponds to that theta. For every theta, there's exactly one point that corresponds to it on the circumference of the circle. Here comes even more fun stuff. Well, we just showed that cosine theta is equal to x and sine theta is equal to y. And I'm recalling this thing I wrote on the board a moment ago. Sub in. Watch what you get. You get cosine squared theta plus sine squared theta equals 1 squared, or 1. But this is the very famous Pythagorean identity that you learned about. Okay? Now, why is it called the Pythagorean identity? Because the equation of the circle comes from Pythagorean theorem. So that's why this thing has been told to you. That, hey, this is the Pythagorean identity. Your teacher told that to you, and you may or may not know why. Okay, so if you had a teacher who showed you, that's great. If you had a teacher maybe who didn't have time to show you, now you know. Right? Okay? Now there's another identity hiding in here. We worked on cosine. We worked on sine. What about tangent? Well, tangent theta, according to this picture, is the opposite y over the adjacent x, y over x. But we just showed that y is really sine of theta and x is really cosine of theta. So now you know why tangent theta equals sine theta over cosine theta. While we're speaking of tangent, this might be a nice time to discuss the following. Why is it called tangent theta? Sometimes what people always want to know is, this tangent trig ratio has the word tangent in it, but the last time I saw the word tangent, I saw it in a situation like this. I had a circle and had a line go by, and we said if the line just skimmed by the circumference of the circle at one point, it was tangent to the circle at that point. So the question might be, well, how come this is, what's tangent theta have to do with this picture? So that's what we're going to answer next. So let's try and answer this question. So I'm going to do that. I'm going to start off again. I'm going to draw the unit circle again. And we're going to draw that little right triangle we had. Put theta here, right? We showed that tangent theta equals, well, this is the point x comma y here, right? So this is the point x comma y, then tangent theta was y over x. Okay. So again, my goal here is to explain why this trig ratio, y over x, is called the tangent of theta. So here we go. I am going to make another right triangle. I'm going to do it in a very special way. I'm going to take this base here. I'm going to make the base of it out here to the point 1, 0. So my new right triangle, my green right triangle, is going to have this base here. We know the length of that is 1. Okay. I'm going to extend the hypotenuse until it meets up with that perpendicular. Okay? That's what I'm going to do. So, now I'm looking at this picture and I'm noticing, if I just take a minute, if I highlight this line segment out here, now I'm beginning to feel a little bit better, because that looks like a tangent to a circle, doesn't it? Yes. Right? Okay. Let's talk. The green triangle and the red triangle both have a right angle in them, and they both share angle theta. So these two triangles have two angles that match, so they must be similar. So since they're similar, we know that their sides are in proportion. So here we go. Ready? we can say that, let's name the sides. This is x and this is y, right? So we can say that y over x equals blank, right, over 1. So I don't know what this blank is here, right? But it's going to be, I'll call this d for a minute, d over 1. Agreed? Agreed? All right. Now, I don't know how tall this is yet, so I'm calling it d. It's a good letter. But I know that the whole base is 1. I know that 1 and x correspond like y and d correspond. Well, I'm just going to write y over x equals d. But wait a minute. Y over x equals tangent theta. So that means d is tangent theta. So that's the reason why. Okay, you may have missed it. But look, what I'm saying is the length of this tangent line is exactly equal to the tangent of the trig ratio, the tangent theta. And that's why it's called tangent. All right, just a few more things. We had mentioned we got that Pythagorean identity. There's two more that usually go with that, and you can get them pretty quickly. So, like for example, if we took this thing and we divided everything by cosine squared, we divided the whole thing by cosine squared, watch what you would get. Cosine squared over cosine squared would be 1. Then you'd have sine squared over cosine squared. But sine over cosine, that's familiar. That's tangent, right? So that's really plus tangent squared theta equals. And then 1 over cosine theta is secant squared theta. So that's another Pythagorean identity. It literally is just the original Pythagorean identity. You divided everything by cosine squared to make it look different. Okay? And then what else could you have divided by? Instead of dividing by cosine squared, you could have divided by sine squared. So we'll do that one in green. You'd have cosine squared over sine squared. That's really not tangent, but 1 over tangent, or sometimes referred to as cotangent squared theta, plus sine squared over sine squared is 1, equals 1 over sine squared is cosecant squared. So here's two more Pythagorean identities that you've probably seen in the past. That's how you get them. They're quick to get. Okay? All right. Now, let's go a little bit further with this unit circle. At some point, you also probably memorized some special right triangles. Like maybe if you were studying for your SAT, you'd know things like this is x, x, and x rad 2 if the triangle is a isosceles right triangle, or the 45, 45, 90 right triangle. Right? You learned about the 30, 60, 90 right triangle. Across from 30 was x, across from 60 was x rad 3, and the hypotenuse was 2x. Right? And then maybe at some point you had to memorize things like if you knew you had the sine of 45, you had to know that was equal to rad 2 over 2. Or if you had the cosine of 60, you had to know that was rad 3 over 2. Right? So the question is, how can we use the unit circle to sort of derive some of these special values? Okay? So that's what I'm going to do next. All right, we'll look at the case we'll look at this case first. That's what we'll do. All right. So I'm going to draw a unit circle again. Okay. And what I'm going to do is draw an equilateral triangle in a very special way. So I'm going to draw a line like this such that this angle is 30 degrees. And then I'm going to draw another line like this so this angle is 30 degrees. Okay. So if you look at that, what you notice is this entire angle here that I've arced in green is 60. Right? So then what I'm going to do is I'm going to draw this line segment in. Now, let's try and convince ourselves that this green triangle I've highlighted is actually equilateral. It shouldn't be too bad. Right? Well, you know that these two pieces are the same because they're both radii of the circle. As a matter of fact, they both have length 1 if we're on the unit circle. Right? Okay. And what else do you know? Well, you know that in an isosceles triangle, if I draw in an angle bisector, it bisects the base. So this piece is equal to that piece. right? Which makes this upper triangle here, this one, congruent to that one. Well, if they're congruent, then those are both 90-degree angles. And then this angle up here has to be 60 because that's what's left over. So these are 30, 60, 90 right triangles. Here we go. Since this angle bisector bisects the base, right, we know that this piece here, whatever this is, we know that this might be, we can call this x and this x if you like. Right? But we've already showed that this triangle, the big green triangle on the outside, is an equilateral triangle, which means that each of these has to be 1/2 because the whole thing was equal to 1. All right. So now that you have that, you can get this piece. You can get the length of that angle bisector by doing Pythagorean theorem again. Pythagorean theorem is sort of like your best friend, isn't it? Right? So let's call this distance in here, I'm going to call it d, little d again. So we'd have d squared plus 1/2 squared equals 1 squared. That would be d squared plus 1/4 equals 1, or d squared equals 3/4. And if I take the square root, I'm going to get d equals the square root of 3 over 2. And there's that number, square root of 3 over 2. Like, oh, that seems familiar. So let's take one of those little blue triangles out and redraw it. If I take one of those blue triangles, here it is. This is 30, that's 90, that's 60. This is 1, 1/2, and rad 3 over 2. And now you know all your special values for 30 and 60, right? If I want to get the cosine of 30 degrees, oh, by the way, I made a mistake up here. This cosine 60 should have been 1/2. Sorry about that. Cosine 30, you can see now in this picture, right? Here you go. Your cosine 30 would be adjacent over hypotenuse, but that's just rad 3 over 2. Okay? So you can get all these special values just by looking at the equilateral triangle constructed inside the unit circle. Sine of 30 would be opposite 1/2 over 1, which is just 1/2. And now you have all those special things, right? You can do a similar argument by drawing a careful triangle inside the unit circle for this other case. And then you can get the special values that go with that.